Hello everyone. Today I'm going to show you 1D subcritical pitchfork bifurcation using MATCONT. To open up MATCONT, you need to first open up your MATLAB and change your current directory in your MATLAB window to MATCONT folder and type MATCONT in the command window of MATLAB. See a window will pop up naming MATCONT. So first you need to load the system you want to work with. So go to select, go to system and go to new. Name your system like Subcritical pitch. So please don't put any space in your name, in your system name, and give coordinate. Here we are working 1D bifurcation, so our coordinate is x, say, and parameter is r, say, and select first three symbolically and other two numerically. Symbolically integrations a bit slow and numerically it's a bit fast, but you can set first one symbolically, other four numerically also. And here you need to give your system, write down your system. So our system is x dot equals to r star x plus x cube. If you have done anything wrong over here, the system won't load up in your MATCONT. As you can see, the system is being loaded. So first you have to find the fixed points. To find the fixed point, go to type, go to initial point and point. The window will pop up. One window is starter window, and the other one is integrator window. The starter window will give some initial conditions. For t equals to 0, we will give a random initial condition for x and also r. R value you can give minus, you can give plus, no problem. You can give less than 0, and we can give greater than 0. In the integrator window, we just have to do one thing: change the interval to 100. You can set it 1000. It will take a bit more time. And we are done with these two windows. And never close these two windows, because these two windows are very important during the process. And then you have to open two windows. One is numeric window, another one is graphic 2D plot. In graphic 2D plot, you can see option like layout, and go to layout and go to variable on axis. So as we are trying to find the fixed point fast, so we are plotting our coordinate x with time. So we'll see the variation of x with time, and if it's a straight line, we'll know that this is a fixed point. And the point we can see in our numeric window, and we are changing the plotting region right now. So set it from -30 to +30. It's random, you can set anything. You can close this window, and we are all set to see the fixed point. The fixed point value will be shown in a numeric window, and you can see the curve in your 2D plot. So to see the plot, or to start the computation, come back to the MATCONT window and compute and hit forward. As you can see, it's a straight line in your 2D plot, and you can see we are having a fixed point at x equals to this. It is almost equals to 0. So if you have any doubt, so you can compute and hit extend to see, is this really a fixed point, is this value is changing or not. So we are having a fixed point. So to get that fixed point, the curve where the fixed point value is being stored is named as P01. So we'll go to P01. To go there, go to select, go to initial point. P01 last point is our fixed point, so select it. And now you have to tell MATCONT that the point you selected is our equilibrium point. So go to type, go to initial point and select equilibrium. And in the starter window, you can see starter window is a bit changed. You see a radio button beside R. So select R and come back to your 2D plot. Now go to your layout and variable on axis. Now you have to see the bifurcation diagram. Bifurcation diagram is being plotted between coordinates and parameters. So parameters is set in x-axis. So this is our only parameter. So r is set in x-axis and x is fine in y-axis. So hit OK. and come back to numeric window, and you can see option window, go to layout. You can see there are a lot of things, coordinate parameters, test function, eigenvalues is what we need, because eigenvalues will tell us the branch we are getting is stable or not. As you know, real part of the eigenvalues is less than 0, so the branch is stable, and the real part of eigenvalues is greater than 0, so the branch is unstable. So we are all set to see the bifurcation diagram. We don't have to do anything else. Just come back to your MATCONT window, hit compute and hit forward, and look into your numeric window and also your 2D plot. We are having a point called BP. BP proof, you can see in MATCONT window status, its branch point, where the stability has been changed. So you won't have to do anything, just resume the calculation. And you can see there is a branch going down, and the real part of the imaginary value in numeric window is greater than 0. So it's a unstable branch. And you can go on computing like this, compute extend, to see is there any more branch point is there in this branch or not. But there will not be any more branch points. So I will go backward and go to compute and hit backward. You can again see in the numeric window the real part of the imaginary value is greater than 0, so again the branch you are getting is unstable. You can stop the calculation or you can let it happen. Okay, so the calculation has been done, and you can see the upper half of this parabola is saved in EP2, and the lower part, if you have seen the calculation, you can go back and you can see the lower part is been saved in EP1. Now we want the branch along y equals to 0 axis. Now we can directly do that, but the problem is when we plot the bifurcation diagram, EP1 and EP2 data will be overwritten. So to avoid that, we need to change the name of EP1 and EP2. So to do that, first you need to come back your MATLAB command window, and we have to go to the folder where EP1 and EP2 been stored. The folder path is cd system, our name, our file name. So it's subcritical pitchfork bifurcation. This is our name which we have given there diagram. So this is our path where we can find EP1 and EP2. You can see in the current directory the path has been changed, and in your left side you can see EP1.mat and EP2.mat. You don't have to do anything, just right click on the file and rename it. So as it is subcritical bifurcation, so I'm naming them as sub1 and sub2. So they are fine. Now again we have to come back to your MATCONT folder. So you can see current directory is hit in MATCONT folder. Now come back to your MATCONT window and go to type initial condition point. Now as you can see in the starter window, X has been loaded with the our previous fixed point values. So now we want to another fresh integration with a different initial condition along y equals to 0 axis. So we set x equals to 0, and r, you can change the value of r or you can let it as it is. I am changing the value. You can let the previous value there. It won't affect actually. It will change the diagram, but it won't affect. It will change the details, but it won't affect the diagram. So again you come back to your graphic window, that is this, and change the layout. First you can clear the diagram or you can just directly come here, variable on axis. So first we want to see our fixed point analysis. We have to find the fixed point actually. To do that we'll repeat the same process. So first we are setting t time in x-axis and hit OK, and just go to compute and hit forward. And you can see x is 0, so we are having a fixed point as x equal to 0, which has been confirmed by the 2D plot, as x is not varying with time. So we'll again, and this value is stored in PO2. So come to select, go to initial point, PO2 last point, select the last point. You can see t values is changed to 100, x is 0 and r is 3 in the starter window, and tell MATCONT that this is our equilibrium point. Now in the starter window, check the radio button beside R. If it's already checked, fine. And come to your 2D plot. You need bifurcation diagram. So you will put parameter in x-axis. All are done. So come back to compute and hit forward. And you can see the branch you are getting having eigenvalue greater than 0. So this branch is unstable. And you can extend it. You can leave as it is. As you can see, the first value is been stored in EP1, and next value will be stored in EP2. And to have that, to compute and hit backward. As you can see, it started with positive values, but it came to 0, and you are seeing again a BP point, that means a branch point. So again resume it. And you can see the eigenvalues, real part of the eigenvalues is less than 0. So this is only our stable branch. All those branch we got are unstable. So this is our last branch of our bifurcation diagram. So our calculations are all done. We need to merge the total diagram. First the parabola one and this one. So we have to merge that. So to merge that, first we'll come back to our MATLAB window, command window, and we'll again go to the same path where we have gone previously. So this is our path, and you can see all those files, your sub1, sub2 file, and EP1 and EP2. And first we'll load the sub1 file, sub1.mat file. So in sub1.mat file, first go to your workspace, right side of your current directory. You can see there is two matrix, F and X. F matrix contains all your eigenvalues. It is having one row and 300 columns. That means it has having 300 eigenvalues. And X matrix contains two rows. The second row of X matrix contains the parameter values, and it also has 300 values. So 300 parameter values and 300 eigenvalues. So we'll plot parameter values and eigenvalues. So, and before doing that, you have to check the eigenvalues are positive or negative. So if it's positive, then it's fine, we are having an unstable branch. If it's negative, it's fine, then we are having a stable branch. But somewhere starting from 1 to 300, if the value has been changed, we have to find that column where the value has been changed. To find that, first we loaded the file, and then we are checking from F all the rows. That means we are having one row and first column, and X second row and first column. We're checking the value. We set column equals to 1. As you can see, it's almost equals to 0. Now if you remember the calculation, we had our eigenvalues greater than 0, and that branch was unstable. So all those eigenvalues we should get for that file sub1 should be greater than 0. So as you can see, column 10 is also greater than 0. It will go on increasing like this. First value is your eigenvalue, and the second value is your parameter value. We will only look for the eigenvalues. So see, the eigenvalues is greater than 0 for column 100. So we'll check for column 300. As you can see, it's greater than 0. So no problem with this. So we'll plot all those values 1 to 300 for F and also R. So first we put R in x-axis, and R is in second column of X, and all second row of X, and all those columns. And for X, we are having one row which is eigenvalue row, and all the columns. So hit enter, and you can see the diagram. You are having the lower part which you calculated fast, and we will get the second diagram. Before doing that, type hold on. Now load the second file, load sub2 .mat. Okay, again we will do the same process. We'll check is there any where the value is being changed its sign. See, for 10 it's positive eigenvalue, for 100 it is positive, for 300 it's positive, and it is going on like this. So it is also unstable branch. So again plot those values. This is the plotting command. Again hit enter. You can see the total parabola. Now we want the line along y equals to 0 axis and x equals to 0 axis. So y equals to 0, x equals to 0 point actually. So to have that, first load your ep1.mat, hit enter. If you remember, ep1.mat also had unstable values. So again, but we'll cross check it. So first check the first value. See, it's greater than 0. Check the second value, 10th value is greater than 0. Sometimes you can handle value. You can see it's going on like this. So it is also greater than 0. So it is also unstable. So again plot all those values and check the plotting diagram. You have the right side, but see this value is not, this part is not connected. So how we will find that part? So that part is unstable, and the rest of the part of this parabola and the left side is stable. So if we have to find somewhere the stability is being exchanged, so we have to find the point. The point is in our ep2 ep2.mat. Load it and check the first column value. It's positive, so it's unstable. So as you can see, first when we done the backward integration, it started from this point, it go on like this, and somewhere it shown us BP point. So have to find where is the BP point. So check for 10th column, is still greater than 0. Okay, check for 20, it's still greater than 0. 30, 40. See, 40 is less than 0. So somewhere in between 30 and 40, eigenvalues is being changed from less than 0, greater than 0 to less than 0. So check for 35. 35 is positive. So go to 37. I see 37 is having 0. So check 38 and you can see it's less than 0. So 37 is 0. 35 was having greater than 0. You can check also 36 for your convenience. 36 is having greater than 0. So in 37th column the value is changed. So we'll plot from our starting point to 37th point where the value is unstable. So if we plot this, we will have this part left, we will have this part. So see what happens. See, this part is joined. Now the rest of the part is stable, so plot the rest part. And you can have your total bifurcation diagram. So maximize it and go to this option, plot tools. So you can make it look like a real bifurcation diagram as you see in your books. So these are all unstable branches. So select all those branches. Select all those branches and dotted line. It is customary to show our unstable branches as dotted line, and change their color also. Make them red. And this line, and this line is our only stable line, so bold it, and color is fine. So this is your bifurcation diagram. You can have that bifurcation diagram. Yes, the grid is on, and you can see this is your final bifurcation diagram. So thank you all.